Hello everyone, welcome to Civil Learning Online, and today in this video I will be discussing about unit load method. Previously I have discussed about different methods which are commonly used in structural analysis for analyzing the determinate as well as indeterminate structure, and the unit load method is that method which can be used to analyze both determinate as well as indeterminate structure. And the question here given is determine the deflection and rotation at the free end of the overhanging beam shown in the figure. Assume uniform flexural rigidity, means we have EI equals to constant. Here uniform flexural rigidity means EI of each and every span is constant, and we are asked to find the deflection and rotation at free end, means at end C. And in unit load method, what we simply do is we apply unit load at the point where we are asked to find the deflection, and again we applied the unit moment at the same point where we are asked to find the rotation. So guys, before starting the solution of this numerical, I have picked out some important points, and first I would like to deal with the formula which we are going to use in this unit load method. So let's have a look toward the formula. So guys, here I have selected some points, and the first point is, in this method we apply a virtual load or moment of unit magnitude in the direction of deflection or rotation at that particular point. This is the thing which says that we apply unit load or moment of unit magnitude, means of one value 1 in the direction of deflection or rotation, means at the point where we are asked to find the deflection and rotation. In that point case, at that point we apply the unit load and moment of unit magnitude. And the formula for finding the deflection is integration from 0 to L m times m1 by EI dx, and for rotation is integration of 0 to L m2 by EI times dx. Do not get confused or panic by seeing the formula. It is one of the simplest method. One simply needs to have the concept of simple derivative, means we already know integration. We already know integration of x dx will be x to the power n plus 1, x to the power integration of x to the power n dx will be x to the power n plus 1 by n plus 1 plus c, and we will be using this concept for solving this numerical. Isn't it simple? And see here guys, first now we need to know what is m and m1 and m2. So guys, see here, capital M is the bending moment due to the external applied load, means the load which we are given on the given in the question. This is the value of P, and using this P, the value of moment which we calculate is going to be our capital M. Now after this we have small m1, and small m1 is bending moment due to the unit load applied at the point of deflection, means it is the bending moment which is generated when we apply the unit load at the point of deflection. Means here in this question we are asked to find the deflection at the overhanging end, that is end C, means we need to apply the unit load at C, and for using that load we will calculate the moment at different positions in the given beam. And the second and the third unknown is m2, and the m2 is bending moment at any point due to the unit load applied at the point where the rotation is needed to be calculated. And here in this question we are asked to find the rotation at C, means we will be applying the unit moment at the span at the end C. So now without any further delay, let's get started and let's move toward the step 1. So guys, here in step 1 I will be calculating the moment with respect to this load, and for that I will be needing the reaction at A and B. So let us write down solution. And solution, and let us suppose in step 1 let reaction at support A equals to RA and reaction at support B equals to RB. And after this step, let us take moment about A, and let us write down here, taking moment about A. And guys, if we take moment about A, then here the reaction at B is RB and reaction at A is RA. So taking moment about A, what we will have here, RB times, I am taking moment about A, so RB will rotate in anti-clockwise direction, and distance of RB from support A is 3 meter, so RB times 3 equals to, this 50 kilonewton is moving downward, so 50 means here I am using simply sum of anti-clockwise moment will be equals to sum of clockwise moment, and will be equals to all the forces which are taking clockwise direction, means 50, and the distance of 50 kilonewton from support A is 1.5 meter, so 50 times 1.5 will be equals to plus and the UDL is 10 times, means 10 is multiplied by 1 plus 0.5. now the UDL is converted into point load, and now we will need to take the distance up to the CG of this UDL, so 1.5 divided by 2. Now from here on solving this, we will get RB equals to 23.75 kilonewton. Now guys, after getting the value of RB, what we need to do is we need to use one more condition here, that is sum of upward force equals to downward force, means sum of upward force, you can write it here, sum of upward force equals to sum of downward force. And for that, upward force means RA and RB are acting upward, so RA plus RB equals to downward force, means 50 plus 10 times 1.5. now put the value of RB here, and RA plus 23.75 will be equals to 65, and from here we will get RA equals to, here RA will be equals to 23.75 kilonewton, and RB will be equals to 41.25 kilonewton. Similarly, here correct this value, it is 41.25. Now guys, after getting the value of RA and RB, we will move toward the next step, and let us see what is our step 2. So guys, here in step 2 we will be needing a table. This is our step 2, and for in step 2 we will need a table, and here is a table, and there are few points which are to be noted. We need to note down in this table with respect to the diagram which is given in the question. So guys, let us see here. Our first point is span, and in span what we need to do is we have to take all the spans, means BC span. Here we have a point which is E, I have named it this point as E, so second span will be BE, and ED and DA. So let us write down here, span means our first span is overhanging portion, that is CB, means I am moving from right to left, so it will be CB, then BE, third span is ED, and the fourth span is DA. Now after this span column, what we need to do is we have to mark the limit, means the portion from the origin and the end of this span. So that will be our limit. Means limit means the span up to which that span is available. Means see here guys, if we consider, if we see here span BC, then our span BC is starting from C and it is ending at B, and its span is going to be, or it means it is limited up to 1 meter. Means here if it is C is origin and B is the end point, then it is starting from 0 to 1 meter. So our limit is going to be 0 to 1. And before that we can include one more table here, that is origin. So first let us note down the origin here. The origin of span CB is C. Similarly, origin of span BE is B. Similarly, origin of span ED is E, and origin of span DA is D. Now it will be more clear now. See, now we are in span BE and B is our origin and the span of BE is 0.5 meter, means here it is 0 to 0.5 meter, means the limit will be 0 to 0.5 meter. Similarly, for ED we have 1 meter span because it is 0.5 here and it is whole is 1.5, means this much portion is 1 meter up to here. So the limit of ED will be 0 to 1, and similarly the limit of DA will be 0 to 1.5. Now guys, we need to find the moment, and for that let us have a look what we need to do is, so let us draw one more row here, that is of moment, means capital M, means this is the moment with respect to the load which are given on the, which are acting or given in this question. So for that what we need to do is we have to split this span into different sections up to the distance x meter. So let us consider a section in span BC up to distance x meter from C. So guys, if we take moment about this point, then this loading portion is moving downward, this is moving downward, and the span is x meter. So we will have here moment, and down I am taking clockwise as negative, so what we will have here minus 10 times x square by 2. This is UDL, so WL square by 2 is going to be our moment in span BC. Similarly, if we move in span BE, then again what we need to do is we have to take another section here in span BE, and B is here, no? So here I am selecting another section x from B. This is our B, so the section is x meter from B, means origin. So again here we will have moment here, and here the reaction at B is moving upward, so I am taking that positive, and we know the value of RB, which is equals to 41.25. so we will have here 41.25. RB is moving upward and RB value is 41.25 kilonewtons, so RB times x will be our moment. This is moving anti-clockwise, and this whole loading portion up to here is moving downward, so we will need to consider all the loads. So it will be minus, the UDL is 10, and the span from here up to here will be x plus 1 meter. This much portion is our x plus 1 meter, so 10 times x plus 1 square by 2. This is our WL square by 2. Now in span DE, what we need to do is we will again take section x here, but this time we are taking x meter from end D. It will not create any kind of difficulty. You can move from this side also or this side also, but if we are taking moving from this side, then we will need to consider a lots of loads here, and here we have only one point load. So from this end, for calculating the moment in span DE going to be easier, so I am using this step. So guys, here again see, RA is moving our RA is taking our clockwise direction, and this time if we, let me show you a sign convention here. This is the sign convention for moment. And guys, up to here, up to BE, I have used this sign convention, means anti-clockwise positive, clockwise negative, and this time I am going to use this side, this convention, this portion. So RA is moving upward, so it will I am taking this RA positive. So we will have here RA, and the value of RA is 23.75, and the span is going to be 1.5 plus x meter. So 1.5 plus x, and this 50 kilonewton is moving downward, minus 50 times x. So this is the moment, capital value of capital M in span ED. Similarly, if we move in span DA, then again we will need to split a section x in span AD. So we will have here RA, means RA value is 23.75, which is moving upward, means clockwise positive, times x. Now this was the value of moment. So guys, I would like to suggest you one thing, that do solve the equation in this equation in here in this table, so that while finding the while doing the integration, it will be easier for you to find the integration. I will show you further in the steps while calculating the integration the importance of solving this equation in these forms. Now let us calculate the value of a small m1, and if you remember, I would like to remind you that small m1 was the moment due to the unit load applied at the point at which we were asked to find the moment. What we need to do is we need to calculate the moment by applying the unit load at the end C. For that, I will need to draw a span removing the load which we were provided in the question. So let us have a look how the span looks. So guys, for calculating the moment M1 using the unit load, I have removed all the extra applied loads which we were given in the question, and I have simply applied the unit load at point C, at which we were asked to find the deflection and rotation. Now what we need to do is we need to calculate the reaction at support A and B due to this unit load, and again we will take moment about A. So taking moment about A, and let the reaction be denoted by RB dash. So RB dash, and the whole span was 3 meter, so RB dash times 3 equals to 1 times, so span up to here is 3 meter, and this span is 1 meter, so RB times 3 equals to 1 times 4 meter. So from here we will get reaction at B equals to 4 by 3, and similarly reaction at A will be equals to 1 by 3. Subtracting this value from this total load, means 1 minus 4 by 3 will give us 1 by 3, which will be negative, means the reaction at A is acting downward 1 by 3, and reaction at B is 4 by 3, which is acting upward. Remember the sign, we will need this sign while finding the moment. Now guys, again while calculating the moment in span CB, we need to split this span CB into two spans, and let this point be at distance x from end C. So what we will have here, we will have if we take moment about this point, then this 1 kilonewton is acting downward, so this will be minus 1 times x. So let us write down here moment m1 equals to minus 1 times x. Similarly, if we consider the span BE, then what we will have here again, let this be a distance x from B, then and this span is 1 meter. So 1 plus x means 1 times 1 plus x, and this reaction will be negative, and the moment due to this reaction will be positive, and this load and the moment due to this unit load will be negative. So what we will write here, 4 by 3 times x minus x plus 1 times 1, because the distance of this unit load from this point is going to be this 1 plus x. Now guys, again split this span DE and consider, take moment about a point at distance x from D. So again, if we take moment about this point, then also guys, as this reaction at A is moving downward, so its moment will be minus 1 by 3 times span up to this point will be equals to 1.5 plus x, so 1.5 plus x. Now in span DA, again consider this distance x from in A, and taking moment about this point, we will have here minus 1 by 3 times x. Now guys, time to calculate m2. Again here, for ease in calculating the integration, I have solved this equation here, and in step for calculating the m2, what we need to do is we have to apply unit moment at the support C, and guys, I have applied here 1 kilonewton meter, and the effect of this moment 1 kilonewton at support C will be up to point B only, and as it is moment, we do not need to multiply this 1 with this span. So here in span CB, the moment will be equals to unity, and which is moving downward, so it will be negative, and the effect of this unit moment will not be felt in span BE, so it will be 0 0 0. And this was our unknowns which we will be using in calculating the deflection and rotation. So now let us use the formula and put down all the equations and then calculate the final answer, and that will be our final steps. So guys, if you remember the equation for finding the deflection, what we had deflection delta equals to integrate 0 to L m times m1 by ei times dx. So guys, let us find the deflection at y. So deflection at y, and if we move through this span one by one, means for first span CB, then we have the value of capital M and M1. So it will be integration of, put down the limit, and the limit of span CB is 0 to 1 meter, so lower limit is 0, upper limit is 1, and capital M means capital M is our minus 5x square times M1 is our minus x here, minus x, so times minus x divided by ei times dx plus integration of, we will be taking each span in a sequence. So our second span is BE, and the limit is 0 to 0.5, so 0 to 0.5, and the capital value m and the value of capital M is 31.25 times x minus 5, x square minus 5, and this is multiplied by m1 means x by 3 minus 1 divided by ei plus integration of span ED, and the equation is, and sorry, first limit is 0 to 1, 35.625 minus 26.25x, and it is multiplied by the value of m1, which is equals to minus 1 by 3 times 1.5 plus x, and whole divided by EI. We have one more span remaining, that is dA, so I am writing it here, plus dA, and the value of capital M is 23.75 times x, which is multiplied by minus 1 by 3 times x. So guys, now first let us multiply these equations, and then we will integrate and then put the limit. So on multiplying we will get these equations. Now let us integrate this value. Then we will have here 5 x to the power 3 means x to the power 3 plus 1 means 4 divided by 4 EI, and we will put the limit 0 to 1 plus. Now on solving this equation we will get on adding these like terms we will get a equation, and then we will again integrate it. I will show you here. So this was the equation which we got on adding the like terms here. Now let us rewrite this term here. This is 5 by 4 into x to the power 4 by EI plus, and if I am integrating this, then we will have here 1.67 x to the power 4 by 4 plus 15.42 x to the power 2 means x to the power 2 plus 1 will be equals to 3 by 3 minus 32.92 x square by 2 plus 5x, and the limit will be 0 to 0.5. Similarly, adding here 8.75 x to the power 3 by 3 plus 1.25 x square by 2 minus 17.81 x, and the limit is 0 to 1. Let me show you here. Limit is 0 to 1. Now after this, here we had EI, and this value is minus 7.91 x to the power 3 by 3 x to the power 3 by 3 EI, and the limit is 0 to 1.5 EI, 0 to 1.5. Now guys, simply just put the value of upper limit, because on putting the lower limit equals to 0, all will be equals to 0. If we put 0 in each and every equation, all is going to be 0. So simply put the value 1 here, 1 x equals to 1, x equals to 0.5, here x equals to 1, and here x equals to 1.5, and calculate the final answer for the deflection. So on putting the upper limit in each for each value of x, then we will get the final answer, and this is our deflection at C. Now time to calculate the rotation at C. So let us see how to calculate the rotation. So we simply represent rotation at C equals to theta C, and if we remember, if you still remember the formula, formula for calculating rotation was integrate 0 to L capital M times small m2 by EI times dx. So guys, here the value of m2 in these three span is equal to 0. We have the value of m2 in span CB only, so we will multiply this equation by this equation. So we will have here a deflection at C equals to integrate limit of span CB is 0 to 1, and capital M is our minus 5 x square times m2 is minus 1 by EI times dx. So on solving this, what we will have here, 5 x square by EI integration 0 to 1 dx, 5 x to the power 3 by 3 EI 0 to 1. On putting the upper limit and lower limit, we will have a 5 by 3 EI. This is our the final solution for calculating the rotation at the free end C. And I hope you enjoyed today's lecture, and I will soon be back with the new topic. And till then, stay safe and take care of yourself. Do like and share this video. See you in the next video.